Uh, let's see. When did that come? Got to send out an email really quick to a student who's on the wrong Zoom, it looks like. Maybe I just get him to the right Zoom. All right, let's see. Oh, it's the wrong class. Let's go to the right class, shall we? All right, we're waiting for one more person, I think. All right, it is official at this point. This class is going to be run like a normal class. So we will be meeting 3 times a week, Monday, Wednesday, Friday. I've got the okay to do that. Next week, hopefully I will have lab kits coming out to you next week. I will need, for those of you not on campus here, I will need you to send me an email. You can send it through WebAssign or you can send it directly to my email account. I need your address that I can send the lab kits to next week. Also, just as a reminder, exams will have to be taken with a proctor, either on a campus, either on a North Platte Community College campus or Mid Plains Community College campus. We have, of course, 2 campuses in North Platte, but we also have campuses in other locations: Valentine, Ogallala, Broken Bow, Imperial, McCook. I think that's all of them. But anyway, you can take them there, but you can also go to a public library or have a professional educator, a teacher, or somebody else who works at a school act as your proctor. If you're not going to use, well, whatever you're going to use, if you're coming on campus or you're using some other proctor, you'll need to eventually tell me who that is too. So you'll need to be kind of for the next few weeks looking for somebody to figure out where you're going to take your exams, choosing that person and sending me an email with their information, what their name, their job title, and their contact information, email, phone kind of things, so that I can send them the instructions and passwords. We don't want to be scrambling to do that the week of the exam. So Those are just some housekeeping things before we get started here. Does anybody have any questions so far about anything that you've encountered in WebAssign, or anything from the syllabus that you've thought about, or the class in general? As we talked about them on Monday and Wednesday. Anybody have anything of importance? Okay. Still waiting for one of our students, but we are recording, so I think we'll go ahead and get started here. Today we are going to burn through chapter 1 really quick. Shouldn't be too challenging to get through it. We're covering some basic ideas about what physics is, using different units of measure and standards, unit conversion. We'll talk about dimensional analysis a little bit, estimating and approximating things. We'll talk about significant figures and the basic method for solving problems, not just problems in physics, but really problems in anything in your life. There are some pretty basic tools you can use to do that. I love that they use this image of a galaxy to start off this thing. This is studying space and studying the origins of the universe and the evolving universe is one of the major fields of physics, fields of study in physics, astrophysics, astronomy, cosmology. They all cover these things, and they're fascinating. They're so fascinating that I still love to go and read things about them, watch videos about them, talk to people that are experts about these things. I just bought some telescopes. I've got, I think I've got 15 telescopes at this point. You can see a couple of them in this room, and I've got a bunch of them in the storage room in the back. And I love to go out and look into the stars. One of the things that's most interesting, I think, about looking into space is the idea of time, because we see light. Our eyes detect light of a particular wavelength, but all light travels through space at the same speed as far as we can tell. And it takes time for it to travel through space because there's long distance, because there's any kind of distance. All things take this time to traverse the distance. So as you look out into space, you're not actually seeing things as they are. You're seeing things as they were. For some things, like if you look off into the east, into the night sky, you can see Jupiter and Saturn rising above the eastern horizon, probably around 9-ish at night, 9:30 maybe. And they're quite bright, very, very visible. With a pair of binoculars, you can see more detail. You can see some of the moons of Jupiter. With a small telescope, you can really see the moons of Jupiter and see the rings of Saturn. With a bigger telescope, like the one I just bought and the one I just took out last week, you can actually see the clouds on Jupiter, and you can see real detail with the rings of Saturn. And you're seeing Jupiter not as it is right now, but as it was like 45 minutes ago. It takes 45 minutes for the light to travel from Jupiter to us. It takes 6 minutes for the light to travel from the sun to the Earth. For Saturn, it's over an hour. It's almost twice as far to Saturn as it is to Jupiter. And so on. You know, you go all the way out through the planets. It takes longer and longer for that light to reach us. It's like 3 or 4 times as far to Pluto as it is to Jupiter or Saturn. And maybe even 10 times, actually. I think it's more like 10 times as far. And that's so far away that hardly any of the light actually reaches us, because remember that, well, you may not know this, but light travels in straight lines. So every bit of light that comes from Pluto, if it's not pointing directly at us, it's never going to hit us. If it's pointing even a little bit off center from the Earth, it's going to miss us by a long shot as it travels all those many millions and millions of miles from Pluto all the way to here. So it is definitely definitely an interesting thing, I think, to look up in the sky. You can't see Jupiter with the naked eye, I mean Pluto with the naked eye at any time, really. It's so far away. You have to use a telescope. And when you do see it, it is super dim. It is a very, very tiny dot of light with very, very little brightness to it at all. And it just so happens that right now, the Earth and Jupiter and Saturn are all on the same side of the sun. So we're pretty close to Saturn and Jupiter. We can really see them bright and close. And if you're looking at other things in the sky, for example, Vega is a star that's, I want to say it takes about 30 years for the light to come from Vega. And that's a lot further than 40 minutes. So that's a lot further away. And then you have stars inside of our galaxy. Our galaxy is a big group of stars. And then there are galaxies like this that are further, the closest galaxy to us is twice as far away as our galaxy is big. So you get outside our galaxy, skip a bunch of space that has pretty much nothing in it, as far as we know. And a big chunk of space that's the size of our galaxy, which is quite large. You skip a big chunk that's as big as our galaxy, or maybe even as much as 10 times big as our galaxy. And then you reach the next closest galaxy, right? And that one is so much further away. It starts to become, it starts to become distances that are measured in the number of years that it takes light, or millions of years, or even billions of years that it takes light to get to us. So it becomes a long ways away. The things that are in the sky that are the furthest away that you can see with our eyes are not really that far away in the scope of things, but with big telescopes, you can see stuff that's billions of years away in light terms, as far as the light taking the time that light takes to get to us. And they're now building the biggest telescope they've ever built. It's actually already built, and they're getting ready to launch it into space. It's called the James Webb Telescope. It's about 10 times bigger than the Hubble Space Telescope, which currently is one of the telescopes that has looked deeper into space than any other telescope. This just kind of gives you an idea of the scope of what we're seeing, of what you're seeing when you look into the sky. I have a poster of this outside of my room. This is called the Hubble Deep Field. This is one of the first things that we saw when the Hubble Space Telescope was turned on for the first time. And let's see if I can just do this here. Open image, there we go. Where did it go? Apparently it didn't do what I wanted it to do. Oh, there it is, okay. So this is what the Hubble Space Telescope saw when it was first turned on. When they first put it up there, it actually they discovered that they'd cut one of the mirrors incorrectly, the main mirror actually. So they couldn't see anything. It was just blurry stuff. But then they went up and fixed it. They kind of gave it a prescription. They gave it eyeglasses or a contact lens, whatever you want to say. They gave it a correction, and then they turned it on for the first time, and this is what they saw. But this is misleading, because what they actually did was they pointed the Hubble Space Telescope at a very tiny point in the sky where they had never ever seen anything before. In other words, they pointed it at a dark point in space that had never ever had anything show up in it before. And they just parked it there for like weeks. And this is what they got. Each one of these dots of light and big things of light is not a star. Each one of them is a galaxy. And this was just one of those little points in space. Ever since then, and the Hubble Space Telescope was put up in the early 90s, I want to say. maybe late 80s, but early 90s. Ever since then, they've just been pointing it at other different points in the sky that have never been discovered, and discover the same thing in every little point of the sky. There are just gazillions of galaxies filling up the sky out there. And they are looking so deep into space that they have to park it there for a week sometimes just to gather enough light to see what we're seeing here, because it's so little light coming from such a long distance away. They're looking 5, 6, 7 billion years into the past at this point. What we're seeing here is not galaxies as they are now, but galaxies as they were 5 billion years ago, before the Earth was even formed. So it's fascinating to me to think about these things when I'm studying science, because there's so much we don't know, so much we're just learning, so much to understand. We start with the very basics in this course, but as you go on into engineering, you will get more and more into the more complex things. You will take other physics classes that are more complex. You will take many engineering classes that are very complex. And eventually you may end up in one of these fields, in one of these sections of your field, where you're actually looking at the very newest thing, maybe working with it to design something, or maybe even discovering the very newest thing. And since you're all electrical engineer hopefuls, those things are actually, there's so many things going on in electronics today. It's just crazy, the things going on in electronics. One of some of the more interesting things I think going on in electronics are probably bioelectronics are absolutely fascinating. Organic electronics. You may have noticed in a store at some point, Sony has an OLED TV out there. It's an organic LED TV. So they're using organic material. Why do we care if they're organic? Well, the materials that we use to make televisions now are maybe not as plentiful. Organic materials are much more plentiful on Earth. Organic means that it's carbon-based. I really want to get a sticker for my car that says only uses organic fuel, because gasoline is also carbon-based and it's organic. Make people think that I'm doing something great for the environment. Because that's how people have tend to take scientific words and make them mean something else entirely. And organic is one of those words. Purely organic lettuce, organic farming. Yeah, you could fertilize your farm with gasoline and it would still be organic. But never mind that. All fertilizer is organic, but what they mean is that, they put horses in the field and made them poop or something. Actually, what they really mean is that they're lying about what they're saying. It's not any different than any other food. It's just making people feel better about eating it. And you can charge more that way too. That's truly what's happening. Anyway, the point being is that science is fascinating. We're at a great time where the technology is really advancing very quickly, so that we can do many of these studies and make more discoveries per capita and per second than many other times in history. We can take advantage of these times to learn and to grow and to really reach out there into the universe. It's an exciting time. I fully believe that within your lifetimes, we will put a person on Mars. It'd probably be pretty close to the end of your lifetimes, in my guess, but it's very possible, and that'll be exciting to have something like that happen again. I haven't had anything happen like that since I was a kid. I was a little kid. It was the last time we put anybody outside of the orbit of the Earth. So that's super exciting, and it's so much more exciting than going to the moon, for example. And then, within your grandchildren's time, we might even be off to places like Jupiter or Saturn or something. Jupiter is the most likely. It's much closer, of course, but it also has a moon, or maybe multiple moons, that we could get things that we need to get back, like water and fuel, things that are absolutely necessary for life that are just not very plentiful out there in space. And other things, there are many other things that are just as exciting happening right here on Earth. Have any of you heard of the LIGO Observatory or the LIGO Array? Yeah, heard of that? So the LIGO array, LIGO is an acronym for light integrated gravitational observatory or something like that. I don't remember, or something. Yeah, well, it's not, they're not. So graviton, this is, I think that the LIGO array, I think it stands for, I don't know what it stands for. Gravitational observatory is the last two. I can't remember what the first two are. Let's look it up. LIGO. So here is a picture of the LIGO. There are actually 7 or 8 of these now. Here's some pictures of them. They're very long and large facilities. So this is the retroreflector building here. Then they have these things there out here that are like a mile long. They're essentially just long tubes. And you can see there's another building out here, and kind of well, yeah, there's another building out here, and there's another one on this arm that you can't see. The basic idea of this, the LIGO array, is that you've got a laser that is starting off right here, and it goes into this reflector building, splitter building, and it splits the laser into 2 beams. One goes one way, one goes the other way. The building that's halfway down, or not halfway down, but part of the way down on each of these, is actually what is called a Fabry-Perot. It's a Fabry-Perot interferometer, and it's essentially a kind of a mirror. It's a half reflective mirror, so the laser can go through it from the backside. But when it bounces, then at the end there's another mirror, so the laser bounces off the end mirror, and then it keeps bouncing back and forth between that middle building and the end mirror, and that kind of creates the effect that end mirror is actually maybe 100 times further down the road than it actually is. It just creates a longer path for the laser to travel. So these things, you've got these 2 lasers that are traveling, in essence, hundreds maybe of miles in each direction, and that's a 90-degree angle to each other. Right? And then they get reflected back, and they get recombined back at this main building at the crossroads, and then they get sent to this detector over here. So you have 2 lasers that have gone on different paths. They started as the same laser. So they're 2 waves that are the same exact wave, and they're in sync with each other perfectly. Then you send them off on these long paths and bring them back. And before you start using this, you tune this thing perfectly so that the lengths of the paths are the same. So you adjust the path of one of them so that when they're coming back, they're right back on top of each other again, perfectly. And then you just sit and watch and see what happens. And what they've seen happen is that these lasers get out of sync every once in a while. They get out of sync every once in a while, and yet the lengths of those 2 paths haven't changed. And they have all kinds of things to account for, minute disturbances and whatever else. They have all kinds of things to correct for that. But the whole idea of this was to detect whether or not space was constant, because Einstein said it isn't. Einstein, when he came along, he said space is changing all the time. In other words, the fabric of the universe is stretching and twisting and bending and vibrating and all this stuff. He said, it's just not constant. A meter is not always a meter, in other words. Even if it's perfectly the same meter, it's not always a meter because the space that meter is in is changing. Why would it change? Well, it would change when there are gravitational waves traveling through the universe. Gravitational waves are a theoretical thing that came out of Einstein's theories that say that when things that have mass move in the universe, they bend the universe with their gravitational properties, essentially, and they create these waves of gravity in the universe. The universe actually vibrates with these waves. It's a weird idea, but nobody was able to prove it would be correct or to even demonstrate that it might be correct until now. And a few years ago, they built these things and they turned it on to test it, expecting not to see anything because it was just testing it. And they saw right away a wave. And after they kind of analyzed it a lot and tested it and repeated the experiment again and again to see if it was really what they were thinking, they actually determined that it was an event that happened in space a long ways away from here. where two black holes actually collided with each other. They were orbiting each other because of their gravitational properties. And eventually they got so close together that they formed a single black hole. And that sent out a wave big enough throughout the universe that it was detectable on these rays. Gravity waves are very difficult to detect. So the only thing that we're going to see are big events. Small events like you and I coming into this classroom, not going to be big enough events. Now, if I eat a few more tacos, then maybe, because I'm getting big. But anyway, the point is that they've detected this insanely weird thing about the universe, and they've determined that the universe is not constant, according to these theories. Now you think, oh, but that could be explained away lots of different ways. Well, maybe. We haven't come up with any yet, but this is the best explanation for this. And it was a theory to begin with, but now it's been tried and true. It's been confirmed that this is working out this way. And why do we care? Well, because we want to know things about the universe. We want to understand the universe. But if you've ever been a fan of like space science fiction movies, this is the first step into understanding how to go into space and travel through space. We've hardly even broken out of our Earth's gravity. We haven't really. We've sent spaceships out beyond Earth's gravity, but no people. People has only been as far as the moon, and the moon is definitely within the Earth's gravitational influence. So we've hardly gone anywhere at all in the universe. We've hardly gone anywhere at all, even in our own solar system. We're hoping hopefully to go to Mars soon, but it's going to take some more understanding to get outside of our solar system, to visit another star, to go that long, to go that far away. To travel to the next star would take so long. Traveling at the speeds that we think that we can travel at, just traveling by propulsion, rockets or something. You would have to have a ship that had the ability to support multiple generations of people. It would take that long, maybe hundreds of years, maybe thousands of years to get to the next star, the next closest star, which is kind of ridiculous. That's not the way it happened. That's not how it happens in sci-fi films. They just push a button and get there. Well, that button represents an understanding of nature that we don't have yet. That warp speed or that light speed or that other speed, whatever it's called, whatever the hyperspace or the hyper jump or whatever it is, that represents something we don't understand about science that maybe we can learn by understanding the nature of the universe. Right? That maybe we can understand by just figuring out weird things like this. So it's exciting to me. It's exciting. It's exciting to me to watch you guys go off and start your careers and maybe get to be involved in something exciting like this. Oops. Physics studies all of those things, those great big things, but physics also studies very practical things, right? The GPS system is completely a physics thing. To know where you are on the earth, you have to know precisely what time it is where you started and what time it is where you finished. If you don't know those two things, you cannot figure out where you are on the earth. So you need a really high precision, reliable clock. And we use a fountain clock, which uses atoms. There's little vibrations going on in atoms we'll learn more about next semester. But those vibrations are essentially the tick-tick of the clock. And those vibrations are super fast. And as far as we can tell, they're pretty consistent, right? You need a consistent vibration for a clock. On a big clock or like a grandfather clock, it's that pendulum swinging. And it stays pretty consistent. But if you've ever been around a real grandfather clock, you know that you have to wind it. That's what those weights are inside the clock. You have to lift those weights up to the top. They reset a spring. And then as they slowly fall down, they keep that pendulum rocking back and forth. If you have a watch that runs mechanically, for example, if you have a Rolex, it's the same thing. A Rolex has to be wound. In fact, Rolexes were famous for making the first self-winding watch. Rolex designed a watch that winds as you swing your arms when you're walking. There's a little spring and a weight in there that winds itself. And so if you have a Rolex and you put it away at night, you actually strap it onto a little thing that rocks it during the night so that it keeps it wound up. And that keeps it pretty accurate, right? You have to have a clock on your ship when you're traveling from Spain to America. It has to be a pretty accurate clock so that you know where you are as you're crossing the ocean, right? To know where you are north and south on the earth is a little easier because the sun, the elevation of the sun above the earth tells you about how far you are north and south. But east and west is all because the earth is rotating east to west. That's all about knowing times, right? So scientists developed a clock that uses a very high frequency oscillation in atoms to do that. Well, how do you know that the high frequency oscillation is constant? Well, you measure it with a more reliable clock. Well, but that's our most reliable clock. Well, okay, so we don't really know. There comes a point when you can't measure how accurate you're being because you're as accurate as you can be, right? So that smallest thing that we can measure, we have to just assume that it's constant. We just have to assume that it's going to be good. And this is one of the reasons that science is not the factual, perfect knowledge thing that everybody says it is. You know, you often get people that say, well, I don't believe in religion because I only believe in facts and things you can prove. So I believe in science. People that say that are ignorant, or they're arrogant and ignorant, one of the two. People who say that know nothing about science. And believe me, I know plenty of scientists who say that. And I believe that scientists who say that know nothing about science. It's unfortunate. Most scientists that are being honest and that are not ignorant in that way have no problem with religion. You know, religion is actually very similar to science because we have to take things that we see in the universe around us and decide whether or not we can determine how they work. And if for the things we can't figure out, we just have to accept them as true. We call these the laws of science or the laws of physics. Physics has many laws. Chemistry has many laws. Biology has many laws. The laws are the things that we observe the same way all the time out there in the universe, and we accept them as things that always happen that way. We're not really sure why they happen that way. We might have some theories or ideas about it, but we just accept them. We accept them at face value and we go with it. We're going to learn about some of those laws in this class. Here's a great example of one of the laws of physics. Of some of the laws that we're talking about, of these things that we just accept. Gravity, right here, is responsible for these kind of streaks going on here. There's attraction between these massive things out in the universe, and they're pulling matter from one place to another, and we can see that as these streaks. It's also responsible for the spirally arms on the edges of this galaxy here, whatever this is. These actually might be nebulae. This actually looks more like a nebula. I don't know what it is. No, those are colliding galaxies. So these galaxies are colliding. Really, they're just getting really, really close to each other and kind of overlapping their gases and stars. There will hardly be anything that actually like runs into each other. There's so much space between all this stuff. But the reason that they're coming closer to each other is because they have mass. And we know from observing the universe that masses attract each other with this thing we call gravity, right? And we don't really know why. We don't know why masses. There are theories, but they're unproven theories. You mentioned the graviton earlier. You said, I think, did you say the word graviton? So the graviton is a particle that is a theoretical particle that comes from a theory, a model. There are models and there are theories. So models are, and models and theories are interrelated and often used interchangeably. The words are often used interchangeably. But as we look into the universe and we see how things are happening in the universe, sometimes we build a model, which is kind of like a simplified version of what's going on out there to kind of help us understand what's going on out there, right? And so we build a model, we put together this model, and the model may be a visual model, maybe a mathematical model, it may be a color model. There may be, you can use anything to make a model. It's kind of like a metaphor. It's like a scientific metaphor, you can think of it as. And the graviton comes from one of these models. The graviton is a theoretical particle that you and I we exchange back and forth when we're attracting each other gravitationally. There is gravity between us in this room, but it's such a small amount of gravity because we have such a small amount of mass that we don't really recognize the pulling, the attraction of the gravitational forces between us. Planets, however, have a huge amount of mass. So we definitely feel the pull of gravity from the Earth. The Earth doesn't feel our gravitational pull at all, hardly. I mean, if the Earth was a person, wouldn't even notice us because we have such a small, tiny mass. But we definitely feel the gravitational pull of the Earth, right? And theoretically, it's because we're exchanging this graviton particle, which is actually a particle of gravitational something. It has no mass, so to call it a particle really is just a word we're using. And it's theoretical. We've never been able to detect one. But we have ample evidence that it could exist for lots of reasons, because there are other particles out there that we have detected. One of them is called the photon. We have detected that particle, and that's what happens when electrically charged things and magnetically magnetized things attract and repel each other. And we have definitely detected the particles that are exchanged when that happens. And so we assume that it's similar for gravitational things. We kind of make this assumption, we make this leap, we create a model, we start to build a theory about how these things are connected. And then we test those theories, we test those models. We test the theories and then we change the model to fit what we learn. So we update the model. So a new model. So that's the idea of models and theories as we're studying science, which is quite different than other sciences. If you've ever taken a biology class or a chemistry class, they talk about the scientific method as being hypothesis, right? You form a hypothesis from what you're observing, which is kind of like an educated guess, and then you test the hypothesis, and then you figure out your results, and then you create a new hypothesis, and this is called hypothesis-driven science. And physicists don't actually do hypothesis-driven science as much as other scientists do. We still do it, but we also have this need to just go out there and discover something. Hypothesis-driven science isn't meant to discover things. It's meant to essentially further your understanding of what you already understand. It's going to increase your understanding of the things that you already have a pretty solid understanding of, to give you more details and more resolution in your models. But this whole model-driven science, you're essentially just going out there and saying, what's going to happen? I don't know what's going to happen. Let's go figure it out. Let's go find out what's going to happen, right? Or maybe you've got a model and you create a theory around it and you say, well, let's see if this theory is correct so we can see if this model is correct so we can figure out what's happening, right? Physicists are much more interested, I think, in the why things happen rather than the what happens. Hypothesis-driven is what happens. Model-driven science is why does it happen, right? So it's a very different way of going about science. And it has a lot to do with the philosophy behind these sciences. Physics is about understanding the universe. That's really what it's about. It's understanding why nature is doing what it's doing. In the words of Albert Einstein once said in response to somebody who said, well, what good is this to anybody? What can we use this for? Einstein said, well, I'm not really into science to figure out the minutia or the why, what we can do with this or anything else. He said, that's not why I do science. He said, I do science because I want to know what was God thinking, right? What was he thinking when he made this universe? And I think that's the best way to describe this. We want to know as physicists why this stuff is happening. What's going on? What is it? Not, if I do this, am I going to be able to, create this molecule? Am I going to, it's a very different approach because of the philosophical thinking behind the two things. One of the things that's important with science is to understand magnitude which essentially means size, right? Order of magnitude, here we're looking at a detection of gold atoms. This is not a photograph or a picture of gold atoms, it's a detection. And they created this detection, or they achieved this detection by shooting electrons at a sheet of gold leaf. Gold leaf is gold that has been hammered out so long and so flat and so skinny that it's only maybe a few atoms thick of gold. It's almost see-through at that point. And it's super thin. Gold is, you can do this with pure gold. It's very difficult to do this with most metals, but with pure gold, you can do it, which is one of the reasons gold is so valuable. But they hammer it out super thin, and then they fire electrons on it. And on the other side, they have a screen where the electrons hit, because they just go straight through that sheet of gold, but not quite straight through. Some of them get steered off a little bit. They get steered off course just a little bit. Some of them get steered off course a little bit more. And as they do that, you put this detector behind it, which is not, you can use a sheet of film, but it won't really work all that well. You want a detector and connect it to a computer. And you can actually, you get a pattern behind that suggests what the gold atoms, kind of the arrangement of the gold atoms, right? And so you can use a computer to analyze that and then create this image that represents what you're seeing. So what you're seeing here is that there's a fair amount of organization in the gold atoms. You can see that they're organized in these kind of linear strips, and that they're definitely kind of in there like a bunch of balls organized in a box, so that they're all, you know, very, it looks like there's kind of a repeating order or some kind of organization going on. And that's definitely true as far as we can tell with gold. So, but the scale of this is super tiny. Each one of these bright circle things represents a single gold atom. And a single gold atom is something like 10 to the minus 10 meters across. So 0.00000000001 meters across. Very, very tiny. The scale of this is super small. And then here we have this picture of phytoplankton. Phytoplankton are these single cell creatures that live in the sludge, you know, slimy stuff in the water somewhere. And they're just these tiny little organisms, but they're so much bigger than these gold atoms. So much bigger. Each one of these cells contains gazillions of atoms in it, each one of them. In fact, you're not even getting close to seeing the molecules here. This is suspended in water, and the amount of water in this space here is molecules, and each one of those molecules has 3 atoms in it. But you are not even close to seeing the water molecules. They're not even as small as the smallest dot you can see in here. The smallest dot you can see in here has gazillions of water molecules in it. The scope is so much different. This is 10 to the minus 10. This is 10 to the minus 6. It's 1,000,000 times bigger than this. Okay, and this might even not be that small. This might be more like 10 to the minus 5, 10 to the minus 4 maybe. But it's so much bigger than this. And this right here, oh my goodness, we're talking 10 to the like 21. So it's like 1 billion, 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 billion times bigger than this. It's so much bigger. So the scope and scale of the universe is insanely wide. You have these very, very tiny pieces of the very fundamental particles of nature. And then you have a galaxy that is actually just a tiny part of the universe. A galaxy with 1 billion star systems in it or something, 1 billion solar systems in it, or more, 1 billion maybe. Just so much bigger than this little thing. And the funny thing is that there's relationships between the atom and the galaxy. The way that the galaxy behaves and the way the atom behaves, there's some small relationships between them, some slight relationships, which is just crazy, considering their vast differences in size. Order of magnitude is the word that we use to describe these changes in size. And it's usually in the exponent of a 10. That's how we usually determine order of magnitude. So for example, the size of this battery is about 1 order of magnitude smaller than the size of this TV screen, because the TV screen is about 10 times the size of the battery, right? The TV screen is about 1 order of magnitude smaller than I am, because it's about 5 or 6 times smaller than me, and that's close to 10, right? What's an order of magnitude bigger than us as humans? Give me an example of something that's an order of magnitude bigger than a human. What's that? A vehicle, a big vehicle, right? So like an SUV, a human, average human is, close to 1.5 meters, 2 meters tall, somewhere in that range. So if let's say you're 2 meters tall, you have a car that's 2 meters, 20 meters. 20 meters would be 60 feet long, which is a very big car. But you can go about half that and still be about an order of magnitude bigger. 30 feet long is not that big. It's still a very big, it's like a bus. So a vehicle would be a bus 30 feet long, a bus 30 feet long, or a bigger bus would be an order of magnitude bigger than that. An order of magnitude bigger than a bus is going to be like, a ship, a Navy ship or something, a big boat. And it's every order of magnitude you go is 10 times bigger. So if you're 3 orders of magnitude bigger, you're 10 to the 3 times bigger, which is 1,000 times bigger, which incidentally is about the difference in size between the atom and the nucleus of the atom. If the atom was a baseball field, the nucleus of the atom would be a baseball sitting on the pitcher's mound. It's 3 orders of magnitude smaller than the atom itself. The rest of the atom is just empty space and random fleas running around the stadium as electrons. Right? So the order of magnitude is something we talk about in physics because of this vastness of the differences between things in the universe. It becomes quite important. And it's very much about rounding as well. So if you're 5 times bigger than something, you just call it 10 times bigger. Right? This has its problems because pi is 3.14. So if something is pi times bigger, right, then it's about 1 times bigger, which is about the same size. So if you're 3 times bigger than somebody else, you're considered about the same size in order of magnitude. But if it's pi squared, well, pi squared is 3 times 3, which is 9. Or 3.14 times 3.14, which is more like 10. So you're actually 10 times bigger if it's pi squared times something. So it has its challenges, but the idea of understanding order of magnitude is about approximating things. And it's important to approximate things. Why is it important to approximate things in science? Why do we need to know how to approximate things? Yeah. So there will be many times in this class when you'll be doing your homework and you'll get an answer. Like, let's say you're getting an answer for how fast somebody was running the 100-meter dash, right? The 100-meter race. And you're doing an estimate for how fast they were moving during that race, right in the middle of the race, for example. And you get an estimate of 100 meters per second. That's your estimate. No, that's your answer. And then you say, could that be correct? Well, is that number too big or too small, just like you said? Did I get it? It's like the 3 little bears, right? Too big, too small, or just right. So you can do an estimate. You can say, well, what was the total distance? Well, the total distance was 100 meters. What was the time? Well, the time, we know for 100 meters is around 10 seconds. There are people that have gone under that. Most people go over 10 seconds, but it's right around 10 seconds for most people. Even for young kids, it's, a little bit more than 10 seconds, not much. If you're really little kids, it might be as much as like 17 or 18 or 20 or something. But for most kids, for most people that are closest to adulthood, it's around 10 seconds. So you take 100 meters divided by 10 seconds, that gives you speed. The average speed for this race should be 100 divided by 10, which is 10. Is it likely that we're going to ever hit 100 if our average is 10 and we're a human being on feet? No, that's ridiculous. So our answer is obviously wrong. We need to go back and redo that problem. Sometimes you will find that your answer is actually right when you do an estimate or an approximation, but that's totally fine. Not sometimes, hopefully most of the time you'll get things right. Here's another example of how you might use estimations. Here I've got a stack of about 200 business cards. Okay. It's about 200. Each business card has ink on it. That ink has thickness. There's a thickness to that ink. If you look at it really closely, you can kind of tell that it has a thickness, kind of, but it's a very tiny thickness. Can you think of a way that you could approximate the thickness of the ink of these cards by using 200 cards to measure it? Can you think of a way to do that? Anybody out there on Zoom, can you think of a way to do that? What if I give you a clue? Here's a place on the cards that has no ink, this corner right here. Notice if I squeeze it, it's actually less thick than the other part of the stack. This is the part side that has ink. This is the side that doesn't. Can you figure out how to do it now? Where there's no ink, it's about 3/4 of an inch. Where there is ink, it's about 1 inch. And there's 200 cards. So about 1/4 of an inch for 200 layers of ink. Take 1/4 of an inch, divide it by 200, get an approximate thickness for the ink, right? That's another thing that you can use with approximations or estimations. There are many different things you can do with this. Now, the other things that we talk about in this chapter I'm only here at the very beginning, but the other things we talk about in this are the metric system in this section here. I'm assuming you've all used the metric system before, but if you need a review, you can go there and do that. But we also talk about unit conversion, where we use a conversion. It's often called a conversion constant or a conversion, I don't remember what people call it, but it's essentially a number 1. It's essentially you're multiplying something by something over something where those two somethings are the same. Like 1 yard equals 3 feet. So if you do 1 yard over 3 feet, that's a conversion. They call it a factor, conversion factor, if you want to convert from feet to yards. And the best way to realize how this is done is that the conversion factor is set up in this little multiplication so that when you multiply it, the thing that you're interested in getting rid of cancels out. Meters divided by meters cancels out. And the thing that you want to end up with ends up being left. I like the way that they do this with these just straight up fractions in here. You can also do this with combined units. Here we have distance divided by time as the speed. And you can convert speed by converting the distance and then also converting the time. They did the time earlier. Here they did the time. So lots of conversions we'll be doing in this class. You'll get plenty of practice with that. Dimensional analysis is a way of using the units in an equation to determine whether the equation is true. If you have an equation that's meant to calculate speed and you're multiplying different things together to get speed, then the units of those things multiplied together should give you units of speed, meters per second, or kilometers per hour, or furlongs per fortnight or something. And that's what dimensional analysis is. And the reason I'm burning through this really quickly is because we're just about out of time, actually. But they're not really that difficult. It's not that challenging to do these things. So if you understand what they are and get a little practice with them, shouldn't be a problem. The last thing that they talk about that has anything to do with math is significant figures. Significant figures are not something I'm going to emphasize in this class a lot, but it's essentially how many digits you're keeping in a number depend on the amount that you're given, because the number that you're given determines the precision of the measurement. So if they tell you something is 4.5 meters, that means they measured it to the half of a meter. They measured it to the tenths of meters and got 0.5. If they tell you that it's 4.50 meters, that means they measured it out to the hundredths of a meter and they got 0. And so that 0 is what they call significant, right? So if they measured it and got a 0, it's significant, but Zeros that come before numbers are not significant because those are just placeholders. Placeholder zeros are not considered significant, but zeros out to the right side of a number are significant. And there are different rules for multiplying them and dividing them. I'm not going to hold you to those. WebAssign sometimes does hold you to them. If you're missing points, losing points because of significant figures, just send me an email and I'll turn that feature off in WebAssign. I think I've turned it off in most of WebAssign, but sometimes there are problems that we catch that I've forgotten. And then the last part is solving problems in physics, which we'll actually cover next week because we'll actually be doing some physics problems next week. So has anybody started the homework at all? Looked at it? Yeah. Okay. So make sure that you're sending me your questions, or you can come in and talk to me in person as well. But make sure that when you have questions, you ask them right away. Don't wait. Send a question by WebAssign. Send me an email, whatever, if you have a general question. But do that right away before you forget the question, and then I can answer that right away so that it's fresh in your mind when you get the answer. If anybody sent me questions last night, I probably didn't answer them because I was quite sick last night. I don't know what my problem was, but my stomach hurt really bad. But anyway, I'm feeling better today, so send me your questions and I'll answer. Any other questions before we finish up? We're done here. All right. Have a great weekend. We'll see you next week.
All right.
Did you have a question out there, or was that just a see you later?
That was just a bye.
See you later. Engineering. See you later.